Next concept, fundamental theorem of arithmetic. What is fundamental theorem of arithmetic? Every composite number, right? Every composite number can be factorized as product of primes. Let us take the first composite number 4. 4 can be expressed as 2 into 2. Normally, if you factorize means 1 into 4 we can write, but we are taking only prime factors. Next 6 I am taking 2 into 3 or 3 into 2. Maybe the order may change, but the factors are unique. The factors are unique. Suppose I am taking 10. I can write 5 into 2 or 2 into 5. The order may change, but the prime factors remains same only, right? So this is called fundamental theorem of arithmetic. Next we can see one example in textbook NCERT, example number 5. So consider the number 4 power n. Consider the number 4 power n. The question is where n stands and n belongs to natural numbers, okay, positive exponent. Check whether there is any value of n while applying any value of n for which the 4 power n ends with the digit 0. The question is, consider the numbers 4 power n, because when we substitute n value 1 2 3 keeps on, and the values will change, right? 4 power 1, 4 power 2 will become 16, 4 power 3 will become 64. It keeps on moving, right? Check whether there is any value of n for which this 4 power n end with the digit 0. So let us take 4 power 1, 4, 4 power 2, 16. It keeps on going, right? Without expanding, without applying n value, shall we conclude the answer? How to conclude means, let us take the prime factorization of, because from the fundamental theorem of arithmetic we just learned that every composite number, since 4 is a composite number, every composite number can be expressed as prime factors, unique prime factors, right? So I can write 2 to the power 2 whole power n can be written as 2 to the power 2n. When we need the unit digit as 0, we need 2 and 5 in the prime factorization, right? If you observe means this 4 power n can be expressed as 2 to the power 2n. If it ends with 0, we need 5, but here in the prime factors, so 5 is not there. Therefore 4 power n cannot end with a digit 0 at its units place, right? So we have one more example, 6 power n exercise question. Will it end with digit 0 for any value of n for all n belongs to natural numbers, right? So if you take the prime factorization of 6, so we may get 2 into 3 whole power n. So here also what the prime factors does not contain 5, right? So 5 is not here. So 5 is not included in the prime factors. Therefore 6 power n also cannot end with a unit digit 0. Okay. Next question, question number 5. Use Euclid's division lemma to show that cube of any positive integer is either of the form 9m plus 1 or 9m plus 8. Okay, so let a be any positive integer. So from the given information we have to assume, we have to take b value, right? So since it is given as 9m plus 1 or 9m plus 8, since this 9 is divisible by 3, I can take b is equal to 3. Why means here it is given that cube of any positive integer is either of the form 9m plus 1 or 9m plus 8. So I am taking b value equal to 3, therefore r will take the value 0, 1, 2, right? So a can be expressed as 3q plus 0, 3q plus 1, 3q plus 2. So first case 1. So let a is equal to 3q. So cube of, right? So cubing on both sides. So what will happen? A cube is equal to 3q the whole cube, right? So 3 into 3 into 3, 27 q cube. I can write this one as 9 into 3q cube. So we can assume it as m. So 9m, such that m is equal to 3q cube, right? Next, case 2. Case 2, it is given a is equal to 3q plus 1. Again, applying cubing on both the sides. So on both the sides we are raising the exponent 3, right? So a cube is equal to, we know the formula, a plus b the whole cube identity, a cube plus 3a square b plus 3ab square plus b cube. So using that we can expand, so let it be a. So therefore 3q the whole cube plus 3 into 3q the whole square into 1 plus 3 into 3q into 1 square plus 1 cube. Okay, so 27 q cube plus 3 square 9, 9 3 is 27 q plus 3 into 3 9 q plus 1. Okay, so from all these first 3 terms I can take which is common, means I can take 9 as common, and I can take which also is common, q common, sorry here. So therefore, so 27 q cube can be written as, so 9 we have taken common, so 3 square plus 3q plus 1 plus 1, right? So I can assume this thing as m. So for 9m plus 1. Okay, so we got the answer. Case 3, I can take a is equal to 3q plus 2. Again a cube is equal to 3 cube the whole cube plus 3 into 3q the whole square into 2 plus 3 into 3q into 2 square plus 2 cube. So we can write 27 q cube plus 3 square 9, 9 3 is 27, 27 into 2 54 q square plus 2 square 4, 9 4s are 36 q plus 8. So from the first 3 terms I can take which is common, means I can take 9 as common as well as q common. So if I take 9 means here 3 q square plus 9 6 are 54, 6 q plus 4 plus 8. So I can assume the entire thing as some m. Okay, so therefore I will get the form 9m plus 8. So come to the question. Cube of any positive integer is of the form 9m plus 1 or 9m plus 8. So let us take an example. Let us take an example. Right, so let us take 4. So 4 cube, 4 into 4 16, 16 into 4 64. When I divide that 64 by 9, and 9 7s are 63, so I will get the remainder as 1. So you can try for some other, you can take 5 also. So if you take 5 means, so 5 into 5 into 5 125. When I divide 125 by 9, so 1 time 9 remainder 3, so we can take that 5. So 9 4s are 36, not possible. I can take 9 3s are 27, so the remainder is 8. So you can try for various example like this. You can take any integer and cube it and divide that by 9. You will get the remainders either 1 or 8, or sometimes it can be divisible by 9 also. So if you take 9 cube means sure it is divisible by 9. Okay, thank you, bye. Welcome back. Question number 4. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m, right? So based on the given information, let us take b is equal to 3. Since it is given 3m or 3m plus 1, I can take b value is equal to 3. Therefore, the corresponding r values are, therefore we know that r value can be greater than or equal to 0 but less than b value. So r will take 0, 1, 2. Therefore, a can be written as 3q plus 0, 3q plus 1 and 3q plus 2, right? So now go to the given. Show that the square of any positive integer, so case 1, I am going to take a is equal to 3q plus 0. So square of, that means squaring on both the sides. That means what? A square is equal to 3q the whole square. Now I can write it as, so 3 square 9q square. So it can be written as 3 into 3q square. So let us assume this 3q square as some m. So the answer is 3m. So m belongs to integers, right, or also some positive integer, right? Next, case 2. Case 2, now I have to take a is equal to 3q plus 1. Again squaring on both the sides, I can write a square is equal to 3q plus 1 the whole square. So which can be written as, so we can use the identity a plus b the whole square, a square plus 2ab plus b square. So using that, so this is a, so therefore 9q square plus 2 into 3 6q plus 1. Okay, so I can take this one as, so I should get the form 3m plus 1. So from these two terms, I can take 3q as common. So here one more 3q plus 2 plus 1. So I can assume this entire q into 3q plus 2 as some m. So answer is 3m plus 1. For all that m belongs to some positive integer, right? Next, case 3, I can take a is equal to 3q plus 2. Again squaring, a square is equal to 3q plus 2 the whole square, so which is equal to 9q square plus 2 into 3 6 into 2 12q plus 4. So I can write 9q square plus 12q plus 3 plus 1. So from these three terms I can take 3 as common. So here 3q square plus 4q plus 1 plus 1. So I can write 3m plus 1 such that m is equal to this part, 3q square plus 4q plus 1. So we can conclude that square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So we can take an example, square of any positive integer. Let us take 4. So what is 4 square? 16. When I divide that 16 by 3, so 5 times 15, remainder 1. So I will get remainder 1. Suppose I am taking 9. So 9 means 81. So 81 is divisible by 3. I am taking 9. So 9 square is 81. So when I divide 81 by 3, how many times? 27 times. Sorry, 20. Yes, 21 times. So answer 0. Right. Suppose if I want to, yes, any integer, if you square and divide by 2, either we will get the remainder as 0 or 1. Right. Thank you.